I'm going to describe an interactive simulation in which we look at a reversible reaction taking place in an adiabatic plug flow reactor. The objective is to calculate what is the equilibrium conversion. So if we look at a snapshot of this simulation, you see what we're plotting is conversion versus temperature. Blue line corresponds to adiabatic reaction. The conversion is linearly related to the temperature change. If I convert twice as much, I have twice the temperature change. And the black line corresponds to equilibrium conversion. So we're looking at exothermic reaction. As we raise the temperature, the equilibrium conversion decreases for an exothermic reaction. If we run to equilibrium, this point corresponds to the equilibrium conversion in the adiabatic reactor, and showing then the equilibrium temperature and the equilibrium conversion. And then we can change the feed condition, so we can change the feed temperature, and we can change the moles of inert. So this is shown with no inert, but inert's going to affect the energy balance, and therefore it's going to affect the equilibrium conversion. This is a case where A reacts to B, so inert is not going to affect the reaction otherwise except through the energy balance. And we can look at both an exothermic and an endothermic reaction. So now let's go to the simulation and observe the behavior as we change these parameters. So here's the interactive simulation. We can change the feed temperature, and if I change the feed temperature, then I move the energy balance. Notice a higher feed temperature results in a lower equilibrium conversion for an exothermic reaction. Can also change the number of moles of inert, so I have no inert initially, and as I increase the inert, then I'm actually increasing the equilibrium conversion because I'm lowering the temperature of the reactor. I'm lowering the temperature because I have more material that needs to be heated, so it has some heat capacity for an inert. In this case, that's the same as the reactants and products. And then I can also look at the plot for an endothermic reaction. Now the energy balance is reversed because reaction will cool down material as it moves through and reaction takes place. And equilibrium conversion increases as you increase temperature for an endothermic reaction. Again, you can look at how the feed temperature and the moles of inert then affect conversion in this adiabatic reactor with an endothermic reaction.